Newton got gravity so well, it helped us get to the moon. Ever wonder about time? Like, do we even really get it? Maybe there's way more to it than we think. His idea wasn't just a guess. It was like a key to figure out the universe, showing that it's way cooler and complex than we can even imagine. How does Brian Cox's idea mess with what we thought about time? And what does this mean for, like, everything? Come check out Brian Cox's crazy new idea about what time is in the universe. There are still tons of mysteries, and some have to do with time and gravity, which are super important to us. Imagine time being weird. Sometimes it's slow, sometimes it's fast. Then there's gravity, holding us down, but maybe it's not what we expect. Welcome to Albert Einstein's world of relativity, where time and gravity get turned upside down. Einstein, a smart guy, gave us a whole new view of the universe with his relativity ideas. He figured out how time acts in different situations, like when you're going super fast. It all started in the early 1900s when Einstein came up with two big ideas, special and general relativity. Special relativity, from 1905, changed how we see time and space. Basically, if you're not speeding up or slowing down, the rules of physics are the same for you, no matter how fast you're moving. This brings up some weird stuff, like time slowing down under certain situations. Think about a light clock in a spaceship going super fast. A light beam bounces between two mirrors. To someone outside the ship, the light beam is going on a longer, angled path. But since light speed is the same for everyone, the outside person sees the light take more time to travel that longer path. That difference in time is what Einstein called time dilation. Time slows down for the person moving compared to the one standing still. Looking at how things change when they're moving super fast isn't just in books. Scientists use huge machines to make tiny particles go almost the speed of light. When stuff moves that fast, we have to rethink time to get our measurements correct. Einstein's special relativity changed how we get time and motion. It says the rules of physics are the same for everyone, even those standing still, which is strange. Usually, we think if you add speed to something, it goes faster. But Einstein said there's a speed limit, the speed of light. Another thing. What looks like it's happening at the exact same time for one person might not be for another if they're moving near light speed. And then there's the idea that things get shorter when they move fast. Plus, there's the famous E equals mc squared, saying energy and mass are the same. This is super important for figuring out tiny particles going super fast and stuff like nuclear stuff. Special relativity isn't just a theory. It's used in GPS every day. Satellites send signals to your phone, and they're moving, so time acts differently for them. If we didn't fix the time, your GPS would be way off. So, time isn't set in stone. It changes because of speed, which goes against what we think. Things like light speed staying the same and energy being mass have been tested a bunch. But it gets deeper. Einstein's general relativity, from 1915, looks at how gravity and space work together. Gravity isn't just a pull. It's space and time bending. Gravity isn't invisible. It's just how space-time is shaped. Brian Cox says to think of the universe as four-dimensional, 3 for space, 1 for time. Big objects, like planets, bend space-time around them. We call this bend gravity. Imagine space-time is a big trampoline. Put a heavy ball in the middle, and it makes a dent. If you roll a smaller ball nearby, it'll go toward the dent, not because something's pulling it, but because of the shape of the trampoline. General relativity shows how things move in space, like Earth going around the Sun in an oval path. According to Brian Cox, this is better than just saying gravity is a pull, giving us a more correct idea of planets moving. One big moment for general relativity was the 1919 solar eclipse. Arthur Eddington measured how starlight bent when it went near the Sun. The bend was what Einstein guessed, which proved the theory. Just like speed changes time in special relativity, gravity does too. Near strong gravity, like around black holes, time stretches. A clock there ticks slower than one in a weaker area. General relativity also guessed black holes, spots so dense that nothing gets out, not even light. The edge of one is called the event horizon, the point where you can't go back. Einstein's general relativity changes how we see the universe. Early on, he made up the cosmological constant, thinking the universe wasn't growing. But when he learned it was, he said the constant was a big mistake. However, general relativity is still key of the Big Bang, explaining where the universe came from. Another thing from general relativity is gravitational waves, ripples in spacetime from big stuff like black holes joining. In 2015, the LIGO people saw these waves, backing up Einstein. Over time, scientists have tested general relativity a lot. From planet paths to light bending to gravitational waves, it's always held up. It might sound weird to say gravity isn't a force, especially since we feel it, but physics always checks and messes with ideas. People like Brian Cox always push stuff. And when it comes to gravity, there are other ideas. One is modified Newtonian dynamics, saying gravity acts different with very low acceleration, especially in galaxies, ditching dark matter. Instead of unseen stuff, they change how gravity works. Gravity also brings up dark matter and dark energy, guessed to explain what we see in space. Some say they're not needed, saying other ideas might explain things better. Some researchers don't believe Einstein's gravity theory and are trying other things, like new particles or forces that could tweak how we get gravity. But science doesn't drop old ideas easily. New guesses need to be strongly proven with tests. Ideas like wormholes and time dilation in a four-dimensional world have come from Einstein's stuff. Stephen Hawking's chronology protection idea says we maybe can't go back in time. New research hopes to see if newer models explain gravity and still match what we know. Even if there are tons of ideas, none have replaced general relativity yet. Challenging ideas is important for science. It helps us get the universe more. And while new frameworks appear, general relativity is still the best way to know gravity. It's great because it's simple and can explain a lot, from planets moving to light bending. Like we said, Einstein's special relativity said time changes with motion. So, how does this act in the real world, like space travel? Space travel is amazing but hard. Space is huge, and Einstein said light speed is the fastest we can go. This makes it super hard to go to other stars. Even with great tech, going between stars isn't really doable. Think about how time acts in space with the twin thing. One twin stays on Earth, and the other goes on a super fast trip to a star. When the traveler gets back, they're younger than their twin because they went to the future. Time is important for space people. Long trips slow down time for them. If astronauts go to other stars and time slows down a lot, they'll age slower than us on Earth. Although it sounds like a movie, it's real because of relativity. Imagine sending a crew to another solar system. Because it's far, the trip takes years, even going super fast. Time goes slower for them on the ship. But back on Earth, a lot more time might pass. Time dilation touches not just humans, but also stuff on the ship. Computers and stuff need time corrections to work right. High-speed space travel also brings problems, like being alone for long, getting radiation, and going crazy. Even daily, we see time dilation with GPS. GPS uses clocks from moving satellites. These satellites have time shifts, so GPS has to fix them. Without it, your GPS would be terrible. So, time isn't the same for everyone. It changes because of motion, making us rethink time and space. Now, why does time only go one way, from past to present to future? This way is key. But why does time act like this? We use entropy to describe it, how much mess or randomness there is in a system. Entropy matches time and usually goes up, pushing time forward. The second law of thermodynamics says that in any set place, mess will grow or stay the same. Things get more random and don't just go back. We see it all the time. A neat deck of cards gets messy when shuffled. Ice melts. Coffee gets stirred. All showing that time only runs one way. But for someone watching from Earth, the light is traveling at a slant. But here is the crazy thing, light speed always stays the same. This means that time looks like it's moving slower on the ship compared to Earth. Einstein called this time dilation. Time slows for the person moving fast compared to someone standing still. Knowing how stuff changes at crazy speeds isn't just something to think about. Guys use huge machines called particle accelerators to crank particles up to near light speed. When things get moving that fast, we have got to change how we see time to get the right figures. Einstein's special relativity updated how we get the universe when it comes to time and movement. It goes against what we think is true by saying that physics rules are always the same. It is not like your everyday life where you think adding speed to something already moving makes it go faster. Einstein's point says there is a max speed, the speed of light. So, what happens at the same time for one person might not for another person moving near light speed. This also brings up the fact that things get shorter. Stuff in motion looks squished along the way they are moving when you look at it from a still spot. And, of course, there's the famous E equals mc caret superscript 2, which shows energy and mass can switch places. This is super important for getting how small bits act at high speeds and things like nuclear fish. Really, special relativity isn't just a thought experiment. It touches everyday stuff like GPS satellites are sending signals to your device, and they are moving. So, time acts different on them. If we did not fix time dilation, you would not be able to navigate that well. Basically, special relativity tells us that time isn't the same everywhere. Motion messes with it, which throws out what we thought about time and space. Main things like light speed being the same and mass-energy swap have been held up in tons of tests. But wait, there's more. Einstein's general relativity from 1915 really gets into how gravity and space-time work. It tosses out the old thought of gravity just being a pulling force and says it shows when space and time bend. So, Brian Cox tells us to see the universe as a four-way thing. 3 space ways mixed with time. In this idea, big stuff like stars, planets, and even Earth bend what's around them. We see this mess as gravity. Imagine space-time as a huge cloth. When something big like Earth sits on it, it makes a bend. A smaller thing close by will roll to that bend, not cause it's pulled, but cause of the bent shape. General relativity gives how things in space go in our solar system, like Earth going around the Sun. According to Brian Cox, this goes over the old idea of gravity just being a pull and gives a way better showing of how planets go. A big moment holding up general relativity was during the 1919 solar eclipse. Sir Arthur Eddington's group watched how starlight bent when it went by the Sun. What they saw matched what Einstein said, holding up the theory. Just like motion messes with time in special relativity, gravity also messes with how time goes. Near big gravity spots, like near black holes, time stretches. A clock by one ticks slower than one nearby. General relativity also tells about black holes. Think of them as very crushed that nothing, not even light, can get away from. The edge around one is called the event horizon. The spot where you can't get away from. Einstein's general relativity messes with how we get the cosmos. He put the cosmological constant in cause he saw the universe as still. But after he found it was growing, he saw the constant as one of his so-called biggest flubs. Still, general relativity stays top to the Big Bang plan, telling how the universe comes from. Another big thing from general relativity is gravitational waves, the moves in space-time caused by bad stuff like black holes or neutron stars merging. In 2015, the LIGO group saw these waves firsthand and backing Einstein's talk. Over time, guys have tested general relativity a lot. From planet roads to light bent to gravitational waves, the plan has held up. Even thought the idea that gravity isn't a pulling force may seem bad, physics checks and messes with things all the time. Folks like Brian Cox push what's up. And in gravity search, other looks stay. One such idea is modify Newtonian dynamics M, which says gravity goes different at low speeds, doing away on dark matter. Instead of thinking up unseen thing, man tweaks how gravity acts. The talk around gravity also touches things like dark matter and dark energy said to show how the cosmos act. Some say these are not need and other ways may tell better. Some looks against Einstein's gravity plan are search over paths, like putting unseen stuff in that could tweak or grow gravity get. For sure, science don't dump things out easy. New tells need to hold tough experiments and watch. Ideas like wormholes and time bends in a four-ways frame have been said as things from Einstein stuff. Stephen Hawking's chrono-talk, for one, puts retro time travel may not work. Studies in watch aim to show if new tel can touch gravity by sure data. Although tons of thing have been said, none have put general gravity down. Checking tough theories are need to go past science. It pushes deep cosmos get. And when new way comes about general gravity stays corner store of gravity idea. Worth it for easy, class and the strength to tell that from planet move to light then being remarkable for its simplicity, elegance, and its ability to explain stuff from planetary motion to how light bends. As said, Einstein's talk-up says time does it with motion. Now, let's see how this plays IRL ESP in space search. Space search is wired but work. The cosmos are huge and light are the most speed. This keeps travel down. Even with tech, spaces are not the same. See time weighs the ship flight. One twin stays on Earth while the other puts for very to start. The back of the find the less of time. Time needs space folks. Days on time they show is fast. Humans the trips a slow time day would be slower. See time weighs that GPS. The space use time for it and if GPS not the time with be right. Now, that why time in one day from to from to. One in time for why the ways. See in the time of way and it's more the time. In every ways the has more or less. The ice is all. In a small cup the look the day for time is one.